let's talk about implicit differentiation, but doing it using partial derivatives. So this is a topic that you previously encountered in single variable calculus, presumably in the first semester. But we're going to look at a new way to do it using our techniques from multivariable calculus. Okay, so here's the type of question that you should have seen before. Let's find dy dx given y squared plus 3x to the fourth y cubed minus tan y plus x equals 0. So what was the old way? The old way was we take the derivative of the with respect to x on both sides, basically using the chain rule. So that would give you 2y times dy dx plus 12x cubed y cubed plus 3x to the fourth times 3y squared times dy dx minus secant squared y dy dx plus 1 equals 0. And then you'd have to do some algebra and basically solve for the expression dy dx. So work that all out. So move all the non-dy dx terms over to the right side, then factor out the dy dx and divide, and you wind up with this. Negative of 1 plus 12x cubed y cubed over 2y plus 9x to the fourth y squared minus secant squared y. So there's your expression for dy dx. And as always, remember that you're going to get something that's an expression in both x and y, because the original formula does not represent y as a function of x. Okay, so there's our old method. Just a quick review. And now we're going to look at the new method. So let's see how this works. So we're going to call the left side of the original equation big F of xy. And now we're going to take partial derivatives. So f sub x, calculating that, you get 12x cubed y cubed plus 1. And then partial derivative f sub y, you get 2y plus 9x to the fourth y squared minus secant squared y. And check it out. Dy dx is just negative of f sub x over f sub y. So negative of 1 plus 12x cubed y cubed over 2y plus 9 x to the fourth y squared minus secant squared y. You can quickly see that that matches what we got before. Now, that's very quick and straightforward. It should be a little bit shocking that what seemed a little tricky before is actually really can be done so quickly and easily. Why does this work? So a quick justification for this little mathemagic. So the original equation we're writing as some function f of xy equals 0. Well, now we need to, 1 second here. Now we're going to take the derivative with respect to, oops, sorry about that. We're going to take a derivative with respect to x on both sides. So on the right side, of course, you're going to wind up again with 0. Starting with 0, you're going to finish with 0. What do we get on the left side? So on the left side, the way similar to with single variable calculus, we think of this as a chain rule. So f is our function f is a function of x and y, and then each of those are themselves functions of x. So using our chain rule, you get that this derivative is df dx times dx dx plus df dy times dy dx. So dx dx, of course, is just 1, and then we can simply solve for dy dx. And you wind up with negative df dx over df dy, just doing the simple algebra. Okay. So when you're doing this calculation in problems, important thing to note, easy mistake to make, you're finding dy dx, but when you're doing the calculation, in your answer, what goes on top is df dx, and what goes on the bottom is df dy. Okay. So let's actually go ahead and apply this for a problem. Right. So find dy dx. Given e to the xy minus cos y equals 4x squared. Okay. So the first thing that we need is we're going to need a 0 or at least a constant on one side so that when we take the derivative, we wind up with 0. If you refer back to the proof, we do need a 0 on one side. So we're going to say our function f is just e to the xy minus cosine of y minus 4x squared, and that equals 0. And now that we've got it set up equal to 0 or even just a constant, now we can apply the nice rule. So we just need df dx and then df dy. So df dx, y e to xy minus 8x, and df dy is x e to the xy plus sine y. And so from that we get dy dx equals, so again it's going to be negative fx over fy. So you get negative of y e to the xy minus 8x over x e to the xy plus sine y. That's it, we're done. So remember which one goes on top, which one goes on the bottom, and also remember the negative sign in front. Okay, so that's a look at the basic case where you've got an equation in two variables. Now, it's actually pretty easy to kick this up to several variables. So if we have f of x, y, z equals 0, it extends in actually the pretty obvious way. So the partial derivative dz dx just equals negative df dx over df dz. And then similarly in the obvious way for other derivative combinations. So let's apply this to a problem. Too far. Okay. So we got the equation e to the xz squared minus y cubed equals 2xy. So now let's find partial dy dx and then also partial dx dz. So first we're going to need our big F. Big F is going to be e to the x squared minus y cubed and then minus 2xy, and that's going to equal 0. Okay, now we calculate our partial derivatives. So fx equals e to the x squared minus 2y. Fy is negative 3y squared minus 2x, and then fz is 2 e to the x z. So now we have all our partials, and now we can just write down the answers. So now we know dy dx is just negative, well, it's going to be fx over fy, which is just going to be negative e to the x z squared minus 2y over negative 3y squared minus 2x. And you can simplify the signs if you like. I'm just going to leave it like this. And then partial dx dz equals negative fz over fx. So that's just negative 2 e to the xz over fx e to the x z squared minus 2y. And that's it. So from an equation, finding the derivatives, either an equation with two variables or an equation with more variables, is actually really easy once you use partial derivatives and use this partial derivative